There.
Are we
All right, now it's
live?
working. I don't know. Are we? Can you hear me?
I can hear you, and there's no lag. It's so exciting.
I'm seeing a little lag, but not like a horrible amount of lag.
It's not the 2.5 to 3 seconds we had last week.
No, we can actually have a proper conversation with each other. So I think this is still a vast improvement. But clearly there's still gremlins somewhere in the internets. So, how are you doing, Pamela? What a tough week in space.
It really was. Last week was pretty horrible between the Antares incident on Tuesday and then Spaceship Two on Friday, and our hearts go out to everyone involved with both of those missions and out at Orbital Systems, or Orbital Sciences rather, and Virgin Galactic and Scaled Composites. It was tough, and we I'd like to point out that there's actually a fundraiser going on to raise funding for the family of the pilot who was lost on Spaceship Two.
Yeah. Are there any details on that? Google it, I guess. I'm sure you can find out.
Yeah, there, and in terms of details on what happened, they've identified that for whatever reason, the feathering device that turns it from a space plane into a badminton birdie decided to deploy early, and that sudden attempt at deceleration just tore it all apart.
Right. Well, I mean, it's still early stages, and so I think, the question, the controversy still right now is whether it was a pilot error, whether it was done as whether it was done automatically. They're still trying to get to the bottom of this. So, it was weird on Friday. We were doing the weekly space hangout, and about an hour before we started the show was when this accident happened. And so it was my first time covering something live, and it was quite an experience. And then we were really fortunate to have Ken Creamer, who was reporting, who was actually at the Antares explosion, and he was there and he gave his first-person account, and it's really riveting. So if you haven't already watched Friday's episode of the Weekly Space Hangout, I highly recommend it. I like to think it was a pretty good episode, and you really get a great description from Ken about what it must have been like to be right there then.
Yeah,
So,
I have to admit, I was going back and forth between watching you guys and watching CNN and watching the tweets go by, and I had a friend on the ground that I was talking with back and forth on iMessage, and it was one hell of a day Friday.
I realized I forgot one thing. If you give me 1 second, I'm going to move a phone, or else there might be problems.
Okay. And I get left alone with all of you. What can I do? It's not like I can corrupt you the way I corrupt other people's children. If you're ever given the opportunity to steal someone's children, teach them to walk around going, exterminate, exterminate. Okay, Fraser's back.
All right. Okay, cool. Well, let's get rolling. So, if people have no idea what it is that they have stumbled into, we're going to be doing a live episode of our weekly podcast, Astronomy Cast. So we will be covering today's episode 356, is Inertia. So we're going to talk about this, and then we will stick around for about 30 minutes. Well, we'll stick around until the end of the hour and answer your questions about space and astronomy. So you can use the Q&A app, and it appears to be working this week. So my additional checks and procedures are working. So you should see, if you're wherever you're watching this video, it's say like Fraser Cain is interacting with the audience, and you can click there, and then you can post a question in there, and if I see them during the show, I'll incorporate them into the show, but otherwise we'll answer some of your questions afterwards. And you don't just have to ask questions about the topic that we're doing. You can talk about whatever you want. So, okay, great. Are you ready to go?
I think so. I never know what you're going to ask, so that's a very hard question to answer.
Do you understand inertia?
I believe so.
Well, then we'll be fine.
Okay.
Don't worry about it. I'll throw you a bunch of softballs. No problem.
Okay.
All right, here we go.
I am pressing record. I have pressed record. It is recording in stereo. Damn it. Why? Okay, pressing record, recording in mono. Hi, Preston.
Also recording. All right, here we go. Astronomy Cast, episode 356, Inertia. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. So we're recording this episode on the Monday after the Spaceship Two disaster, and what a week for spaceflight.
Yeah, it was the Antares incident with Orb 3, and then Spaceship 2 all in 1 week. That was a tough week, but I mean, it all comes down to, they say it's not rocket science for so many different things because rocket science is so damn difficult.
Yeah.
And we have to figure this out, and we're still at that learning to explore stage. The analogy I used with several people last week was we are essentially trying to get to the new world, where the new world is getting colonies above Earth's atmosphere, and we're still at that stage of sending out the explorers, but we haven't yet sent out the colonists, and we're going to lose ships as we go, and this is why they're test pilots. It still sucks every single time, and our hearts are with not just the people who lost spacecraft, but the people who also lost their instruments and everything else between those two different spacecraft last week.
Yeah, nicely said. And we'll be talking quite a bit about this on the Weekly Space Hangout. We'll be unfolding that week after week after week. So we record that on Fridays at noon. So if you want to join us there, that would be great. I want to give a shout out as well. We've got some great communities that are around everything that we do. But one community that's been really great and fairly new is the folks who have kind of come together for the Weekly Space Hangout. It's the WSH Crew. They've created their own Google Plus community over on Google Plus. If you just search for WSH Crew, and a lot of the familiar names that we always talk about. And so if you're a fan of Astronomy Cast, I think you'll probably fit right in home with those folks as well. So I just want to recommend that. All right, well, let's move on. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. This is inertia, famously defined by Isaac Newton in his first law of motion. And I'm sure inertia had something to do with the Spaceship Two disaster when you look at it getting torn apart. A lot of the times, so much of spaceflight has to do with inertia, about getting things moving faster and faster, and all of the orbital momentum.
Okay, I'm going to stop you right there because your description was for momentum, not for inertia, and I think pulling Spaceship Two in is probably bad. Can we try?
Do you want to redo that?
Yeah.
So, what, inertia? An object at rest tends to stay at rest? That's not...
Momentum. No. Inertia has to do with why you use a door handle instead of pushing right next to the hinges.
What? All right, I will record another intro and give that to Preston.
Okay.
So let's just get on with inertia then.
Okay.
No problem. So when you're in giving your introduction to physics, how do you describe inertia to your students?
Well, I break it down and I'm like, okay, so we've got force, which is what you apply to an object to accelerate that object, get it moving through space. And what is resisting your ability to get it moving with that force is the amount of mass that it has.
The amount of math it is required to do the calculation.
Right.
Yeah.
It's the amount of mass that matters. Well, when it comes to getting something rotating, the amount of mass plays in, but it plays in two different ways. It plays in because you have to get that mass moving, but the distribution of that mass varies with how it makes it vary on how hard or easy it is to rotate something. So when you're looking at something's inertia, you're looking at what axis are you trying to rotate it around, where is the force relative to that axis, and how is the mass distributed. So this is the point where I usually pick the burliest looking human in the classroom, and I say, okay, walk over to that door and try and push it closed by pushing 3 or 4 inches away from the hinges. So your rotational axis is the hinges, essentially. You're applying your force a few inches in from those hinges, so you have this little tiny distance, and your mass is spread out over this large sheet that we simplify as pretending it's a rod usually. It's just a really weird shaped rod. You're not going to succeed very well. Now, if instead, and here I grab the most diminutive looking human in the class and I say, come over here. Now, use just the tip of your finger and push as far away from that hinge as possible. Well, here you've increased your moment arm, that lever that you're using to rotate the door. Way easier. So that's one part of it. Now the other part of it is how that mass is distributed. So it's how far you're pushing away from your rotational axis. And the other thing is how your mass is distributed. So this is where I now find the person in the classroom with the largest wingspan, the biggest arms in the classroom. And if I can find the person with the biggest arms and the skinniest body, it works even better. And we have, because we're evil, these small platforms that you can stand on and they rotate. And so I'll get a pair of like 5-pound hand weights, hand them to this long-armed, skinny person, and have them start with their arms all the way out and give them a gentle shove on their hands because that requires the least force to get them rotating, and they'll start rotating. And our platform doesn't have that much friction in it, so they're going at a fairly constant velocity. Or in this case, they have a constant rotational speed. It's not really velocity because they're constantly changing. So now their mass is spread out. They're essentially a rod in the center and then kind of the lamest shell of mass ever. I have them bring in their arms, and because they're tall, skinny individuals, they've now suddenly increased their central mass by a large percent, as in like 5 or 10%, and they start rotating much faster. That's because we've changed their moment of inertia. So the moment of inertia defines how quickly something's going to rotate because of the way its mass is spread out as a function of the force that you've applied to it.
And so this is obviously this idea like the skaters who will hold their arms out, and then as they pull their arms in, they rotate faster and faster and faster. And then, of course, go ahead.
No, keep going.
I was just going to say, and then we see this as well in things like some of the rotational, like the planetary formation, how the in the earliest days of the solar system, how as the gas and dust collected together, it had to maintain its total inertia and would spin up and flatten out as a disk.
And we also see it when a star bloats out to being a giant star, its rotation rate slows down. When it collapses down to being a neutron star, it seriously speeds up. And this is also like your mom's way of checking or your dad's way of checking if an egg has been hard-boiled or not after Easter. I don't know about you, but we always had the great post-Easter mystery of which eggs were the ones that got hard-boiled and not painted and which are the ones that are still raw. Well, if you put a raw egg and a hard-boiled egg side by side on the counter and you rotate them, the one that's solid is going to rotate more readily than the one that's still liquid on the inside.
Right, because it will actually push out to the outside edges of the shell, right, and change the blob around inside the shell and change the inertia. So I guess we already sort of started to move towards it, which is that this is Astronomy Cast, and of course everything needs to have its astronomical connotation. So where in the universe, and I'd love to go back to that idea of these neutron stars, where in the universe do we see inertia really playing out on the grandest scales?
Absolutely everywhere.
All right.
It's
Pick
one
something.
of those things that's absolutely fundamental. It drives students crazy because It requires lots of evil calculus. This is one of those places where calculus comes into play. You have to use all of your advanced maths. There's just certain places that require calculus. And where it starts to become difficult is things like the planet Earth. We don't have a continuous distribution of mass. In fact, if you look at how we wobble because the sun is trying to pull us over, it's exerting a torque on us. When you look at our wobble due to the sun trying to pull us back up straight, it turns out that our moment of inertia is this combination of a solid mass of single density and a point source in the center, and this is because we have this really high density core, and then we have the crust and water on top, and we run into neat things like our rotation rate will change after earthquakes because the mass gets redistributed just enough.
Yeah, people always run the calculations for how much our day has changed after the earthquake.
And so earthquakes, and another one that really affected us is the dam that they're building in China. As that continues to fill up, it may already be completely filled up, but the big dam in China actually changed the moment of inertia of the entire planet.
Right. And I guess in the worst case scenario, this is where the tidal forces start to, the interactions that eventually, given enough time, the sun would tidally lock the Earth to the sun to finally balance out that inertia, right? Slow it down to the point that it's sort of in a perfect spot.
Well, with our moon, I'm not sure it can actually get that far, but what the sun's trying really hard to do is currently our Earth is tipped over on its side 20 some odd degrees, and that how many 20 some odd degrees it's tilted over actually wobbles somewhat. It goes between roughly 21 and roughly 25, and as it wobbles between these two different values, that wobbling, which is tied to the precession of the poles, that comes from the sun trying to get us to be completely upright. And luckily we have this moon orbiting around that's locking in our rotation between those two different bodies. So the sun's never going to succeed in tidally locking us or bringing us upright or anything like that. But it's that interplay between our axis of rotation and the precession of that axis that comes from our planet's moment of inertia.
All right. So we've got the interactions between the sun and the Earth. Where else will we see this?
So as you already pointed out, we see it with the collapsing to form our solar system, and then sticking with our solar system for a minute, we see it in the asteroids. So if you look out at how the asteroids rotate around different axes, you can actually start to slowly get at what their distribution of densities are, what is all of this weirdness in terms of do they have the same stuff on the inside in different places, by looking at the way they rotate around different axes and the way these different axes rotate.
That's really amazing. I mean, one of the things that I always find so kind of almost magical is how that if you have like a planet and a moon, the moon orbiting but once you have those two masses together, you can get at the mass, the combined mass, the individual mass of the objects themselves. But if you've only got one body, it's really tough to get at the mass. But watching it rotate,
you still can't get at the amount of mass, but you can get at the distribution of that mass. The
distribution, the density, and then maybe what it maybe is even formed out of, which is just mind-bending.
And this certain approximations are required, because while you can get at, with all of these wobbles and stuff, you can get at the variation, you can get at the ratios. Well, we know it's probably not going to have anything more complicated than an iron core. So if you know what is the ratio of its core to its outer shell, you can start doing all sorts of neat approximations to get at what that density probably is. It's amazing what you can do if you really do a whole lot of math.
Right, and that's it. You're going to have to crack out some really tough math on this one.
And this is where we're also starting to be able to get estimates of where there's probably underground oceans, because underground oceans will change the moments of inertia of moons. We often, but not always, get lucky enough to see these geysers, these ice volcanoes. But barring that, we also can measure over time, if we have the right imagery, the wobbling of their axes. And these wobbling of the axes can be due in part to the moment of inertia and a variety of different gravitational interplays. So if you have that tilt and you have that precession of the orbit, it allows you to get at the moment of inertia, which might tell you, hey, there's liquid here. It's rotating more like a can of soup than a can of pumpkin filling.
Well, it's like but again, it's like spinning those eggs, right? You spin Enceladus or you spin Europa, and you can watch those movements, and that'll tell you whether something's sloshing underneath there.
And this is a really neat one to get to teach to kids to try and get them to understand it, because you can literally take a can of soup and a same sized can of something more solid like pumpkin pie filling and just roll them down a ramp, and they won't go down the ramp at the same rate. And it gets you at the moment of inertia and how it affects rolling bodies.
Oh, because it's solid, it rotates more evenly, but because with the liquid one, it's more sloshing around and more resistant to the turning.
Now, if you want to make it really complicated, you can do empty can, can filled with a different can in the center and suspended. So like if you do can, styrofoam, rod in the center of the styrofoam, and then do your pumpkin pie filling, now you're starting to get at even more complicated stuff, and you can start to see how all of these different maths start to combine, and that combination of can, styrofoam, rod in the center is sort of the cylindrical version of what a lot of worlds are more like.
Wow. Well, this is great. So keep going. I want to hear some more examples of where this inertia comes up.
So as you get out of our solar system and start looking at the stars as they go through their various stages of evolution, their rotation rate, unless they're eating mass off of something else or losing mass to something else, their rotation rate is pretty much set at the moment of formation. You start out with this big old blob of gas and dust. It's kind of hanging out big and blobby, and then something triggers it to collapse. During that collapse, whatever it was that triggered that collapse probably instigated some sort of a force that set this whole thing rotating. As this whole thing starts rotating, initially it's really big. As it collapses, it's like that ice skater bringing her arms in. And as it collapses, it gets faster and faster and faster. And the center star ends up with the majority of that momentum. Now, as the star ages, it's going to change sizes. It's eventually going to bloat up to be a giant star. And like the ice skater putting her arms out, and in this case grabbing sticks and moving the mass out further using sticks, that's going to slow the rotation rate. Then when the star collapses down, it's going to speed back up. So you have this change in the rotation rate of stars as they change in their radius, and that's all due to the moment of inertia.
The part that's really amazing to me is this idea that every single atom, every particle in the entire dust cloud has its own individual inertia, but the final, essentially orientation and speed of rotation of that final gas disk is when you've added up all of the directions and all of the inertia from all those particles, you come up with this average, because now they're all essentially connected as one big body. And that final orientation is just what you get if you average out the motion and the inertia of all of those individual particles.
And this is one of those quantities that gets conserved in systems. So if you're going to stop that ice skater from rotating, you have to exert a torque somewhere. You have to exert a force at a distance from the rotational axes that acts to stop the rotation. Now, if you're a particle orbiting in a solar system, you have some sort of an angular momentum. Now, at the same time, if you're a particle in a galaxy trying really hard to fall into that central supermassive black hole, you're going to have an angular momentum as well. So it's possible for a particle to have an exact, its center of mass is lined up with the center of mass of the black hole, and it just falls straight on in. That's possible. What happens most of the time is you have a particle that's on an elliptical orbit where a perfect circle is still a form of an ellipse. That elliptical orbit pulls it down toward the black hole, and it has to somehow shed momentum somehow if it's going to fall all the way into the black hole. And that gets shed usually through interactions with other particles, so there's a force enacted upon the particle. That energy, it gets conserved, so it gets turned into things like heat. And this is where you get these really hot accretion disks in the centers of galaxies. That's all the stuff that angular momentum prevented from falling straight into the black hole. Instead, it got piled up into a disk. As it gets piled up into the disk, the momentum has to go somewhere. It goes into heat. And stuff that sheds enough momentum is able to fall all the way in.
Now, I want to let the record show that you're the one who brought up black holes in this conversation, not me. But now that you've opened up the door, let's talk about black holes.
Okay. So
where our comprehension of the laws of physics, start to break down, and inertia, I'm sure, is one of these where you push these ideas to their very limits.
And what's kind of fun is when they first teach you about black holes, all of the equations are for non-rotating black holes. And then kind of at the end of the class in grad school, they're like, and these things actually rotate. And if you do research in this, you'll have to solve it in a rotating frame. And all of us who are observational folks are like, oh. And then the theorists who like to chew on math, they get excited and then they go off and chew on math. And when you compare the rotation rates for that accretion disk as far down to the event horizon as we can get with the predictions that factor in time dragging and everything else, the predicted rotation rates for central supermassive black holes of the masses observed, it all seems to line up so far. So folks who are a whole lot more loving of doing math than I am, I'm a computer girl, people who do that and have figured out predicted rotation rates, the physics matches the observations, and we really can't ask for better than that.
Yeah, we've done a bunch of stories on this. The fact that the most rapidly rotating supermassive black holes are rotating at the speeds predicted by Einstein.
Yes.
And the scary thing here is that it's a significant portion of the speed of light that rotating so quickly that they can't rotate any faster, which is just it's mind-bending.
It's really cool to look at all of the things that are nominally happening down at the surface of the event horizon, which is different than saying it's happening at the surface of the black hole. And I know there's a whole lot of debate on whether or not anything can collapse down to a singularity, but we do know there is mass confined inside of an event horizon defined as that surface where you have to be going faster than the speed of light to escape. I stop talking when we hit the event horizon. But so whether or not you believe it's fully collapsed, up to you. There's a horizon at which we can't observe beneath, and at that horizon, the physics matches the observations.
And one of the other interesting kind of more speculative uses for black holes then is that you can actually extract this rotational inertia out of the black hole. That you can drop objects in, and as it kicks them back out, it gives up a little bit of its inertia. And so you can actually you can slow down the rotation of the black hole and extract energy out until you've stopped it, and then you're going to have to feed it again to speed it back up again.
And I do want to clarify that you're not dropping an object into the black hole, you're dropping an object into the gravitational well of the black hole. So you're essentially gravitationally slingshotting the object. And so some of the angular momentum from the black hole gets transferred to this object that's on a highly elliptical orbit. And so by essentially throwing things towards the black hole that whip around it, gain momentum through the gravitational slingshot, the black hole has to give up some of its momentum. And essentially what this also means is every time we use Jupiter or Mars or Venus or any of the other planets to give a gravitational boost to the velocity of a spaceship, every time we do that, we're actually stealing angular momentum from these planets. But the mass of these spacecraft is so small that it's not perceptible. So we don't actually worry about slowing down Mars every time we slingshot.
Right. If we did it enough, if we did it enough, we could eventually cause Jupiter to crash into the sun because we've stolen all of its orbital momentum.
It's
right.
So
No, because we're slowing. We're lowering Jupiter's orbit. Every time one of our spacecraft uses Jupiter's orbital speed to kick into a higher orbit, it's having to take a little bit away from Jupiter. So it's lowering Jupiter's orbit a fraction.
Okay, that I'll give you. Yeah.
Yeah. So I'm saying that if you had enough spacecraft buzz past Jupiter and use them for those gravitational slingshots, eventually Jupiter would run out of, it would spiral in and eventually crash into the sun. That's all I'm saying.
Yeah, that I'll agree with.
But so one last question, and you've been using sort of the terms angular momentum and inertia and momentum fairly interchangeably. So for people who aren't clear on the distinction between inertia and momentum, because they are very similar, how would you sort of describe the difference?
So momentum is what you deal with when you have a whole bunch of things that collide together. Something that is already in motion will share its motion with another object through a collision. They can either bounce off of each other, in which case when you sum up all of the motions, so mass times velocity, that up to what you had going into the system. So mass times velocity for all of the things that are interacting stays a constant. Rotational inertia momentum has to do with, now you're looking at a rotating system. So when you're dealing with linear things colliding, you're dealing with force. When you're dealing with angular, you're dealing with torque, which is force at a distance away. So momentum says things that are in motion stay in motion, and all of the motions across the ensemble are going to be conserved. Inertia says, I'm going to resist this force you are imparting upon me, and I'm going to refuse to rotate by this amount because of how my mass is distributed. Whereas with strictly linear stuff, it's just the mass sitting there going, yeah, I don't want to move.
So I've got one last question for you, and this is going to get kind of philosophical. But
okay.
Why? Why is there inertia?
And
I think this is, well, but I mean, this is one of the things that I think the Higgs boson, the investigation into the Higgs boson has been helping scientists understand that there is this theory about why mass tends to resist movement.
So what you're trying to get at is the fact that all of these different particles are coupled to a quiescent field that permeates all of space and time. But at the end of the day, it's the ensemble of particles going, yeah, I don't want to move, and I'm locked into this ensemble, and you're going to have to get all of us moving. And the ability to get that entire ensemble moving depends on how tightly clustered there are. The analogies that often get used are, if you have a crowd of friends who are kind of distributed all over the place and you send a famous person through the room, the famous person is going to have a huge pull on that crowd of people. And that's the analogy used for the Higgs boson is the famous person has a huge mass and attracts all the rest of the people around the famous person. Well, with inertia, the way to think about it is, how hard is it to get all your friends moving? Well, if all your friends are spread out all over the room and they're all in their individual conversations, they're going to be a pain in the insert whatever you want to get moving.
Right.
But if they're all tightly focused and all together, a point source of people, then they're really easy to get moving. So the moment of inertia reflects on how hard it is to get that ensemble moving, and the more spread out the ensemble, the harder it is to get it moving.
That's really cool. All right, well, thank you so much, Pamela.
You're welcome.
All right, so I'm going to go with this. Isaac Newton so Preston, here's an intro for you. Isaac Newton defined inertia as his first law. The vis incita, or innate force of matter, is a power of resisting by which every body, as much as it lies, endeavors to preserve its present state, whether it be of rest or of moving uniformly forward in a straight line.
I'm good with that.
All right, like if we can't go with what Newton said, I don't know what to tell you.
No, that's fine. It was just what you had at the beginning was not fine.
Got it. We fixed it. I just fixed it.
Yay! Okay, I'm going to stop recording.
I have already stopped.
Okay, I am saving my recording and closing.
I am exporting. Did you clean up the Dropbox? Because I don't have room in the Dropbox now.
No, I haven't done that. I just got my computer functioning, and then the world blew up on me last week.
Okay. If you could delete some stuff.
Looking for a pen to write on my hand so I can remember to do it.
Cool. All right, I've saved to my local drive, so we'll go from there. All right, let's see what the internet wants us to answer.
I hope I'm amusing the internet by writing on the back of my hand.
Okay. All right. Okay, so Rashan Bukhari asks, since Jupiter is mostly gas and has the fastest rotation period in the solar system, why then the Sun, which is a huge ball of hydrogen, why does it take a month to go around once? Jupiter takes like 13 hours or something like that, and the Sun takes a month.
So it has to do with, does the Sun really take that long to rotate on its axis?
Mm-hmm.
Okay. It doesn't totally work like that. So I mean, the thing to think about is the Sun is so much more massive that you're going to have to exert a much greater force on it to bring it up to a high rotational speed. So it just breaks down to there wasn't quite enough force to get the Sun rotating that much faster.
And I'm trying to remember what it was. We're doing an article about the fastest rotating star at some point, and there's ones that are rotating. There's this limit, and essentially the stars are rotating.
It falls itself apart.
Yeah, and the star will actually compress into this flattened, oblate spheroid, and eventually will tear itself apart if it has to spin any faster.
Right.
And the Sun actually rotates so slowly that it doesn't lose.
It's still oblate, but it's not that oblate.
No, it's literally a perfect sphere. It's rotating so slowly that there's almost no oblation. I don't know what the word is, but yeah. Let's move on. Noel Ruppenthal asks, what is the relationship between torque and angular acceleration? Ooh.
You use torque to create angular acceleration, and so torque equals force times radius, and then your angular acceleration is the torque equals I times angular acceleration, I think, but I don't want to get that wrong. Yeah, torque equals inertia times angular acceleration.
For those of you doing math. Elad Avron says, so could Superman stop and reverse the Earth's rotation?
how is he doing it is the question. So if he's simply flying in the opposite direction around the planet, no. He's too far away from the center to be able to do anything meaningful, even if he had some sort of lever arm. And the idea that him flying in the opposite direction, what they're saying is the tidal forces exerted by Superman on the planet Earth are what's doing all of the torque. That makes more sense. That makes no sense. If you want to make slightly more sense, have Superman grab the top of Mount Everest, which is the longest lever arm you have on the planet, and start pushing on that lever arm. So the tidal force of Superman flying in the opposite direction of the Earth's rotation is not going to get you anywhere. Potentially Superman pushing on Mount Everest, which isn't too far from the equator in the grand scheme of things, will give you enough of a lever arm to maybe do something. I'm not sure if Mount Kilimanjaro is enough closer to the equator to make a meaningful difference.
There's a volcano in Ecuador, which is tall. It was just further from the center of the Earth than either of those. So that would be your best place to go. That's like the furthest away from the center. But yeah, I mean, I guess the gist of that is like, would the air, if he was moving around the Earth so quickly, would the air be acting like a brake?
With the frictional force.
Right. And so, but it would destroy everything on Earth. So I don't think you could end up with a usable Earth.
Yeah, no matter how you do it, you destroy Earth.
No, but if you're traveling, if you're trying to use air, the friction of the air to slow down the rotation of the Earth and then speed it up in the opposite direction, you are going to scour the planet like a... for a month, and you're gonna scour it because you're essentially gonna have the air of the entire Earth moving at hundreds of thousands of kilometers per hour, or whatever's the fastest air will do before it just flies off. So that's all. You're gonna essentially create super hurricanes that would kill everything.
Destroyed our planet. But I mean, at the same time, if you're exerting torque by grabbing a hold of this volcano in Ecuador and rotating the planet by exerting force on this volcano, that's also going to destroy the planet because you're now taking things from going however many bazillion miles per hour they're going on the surface of the planet to zero to the other direction.
But if you do it slowly, if you take
over months and months and months.
Well, yeah, you got 1,000. Well, you got to slow down 1,000 kilometers. No. If you're in an airplane is going, say, it's close to 1,000 kilometers, and it slows you down to zero within a few minutes. So no. If you could slow the Earth, take a month, slow down the Earth, speed it back up. No one would know the difference except the sun is moving the opposite direction of the sky. But time would not go backwards.
No.
Because time has nothing to do with the direction the Earth is spinning. And there's a great episode of Futurama, which you've never seen. It's called something cats. Anyway, I'm sure the Q&A app will tell me in a second here. The gist is they do that. They essentially stop the Earth and they have it spin in the other direction. And for the rest of Futurama, the Earth is just going in the wrong direction. And it doesn't make a big difference, except that anyway. All right, let's move on. Jim Meeker asks, how many hot dogs do we need to slingshot around Jupiter to make it spiral into the sun?
A lot.
A lot. Yeah.
We don't have enough cows.
Could we reuse the same hot dogs? No, probably not. I see. James Oliver asked, how many space probes do I need to get Jupiter to spiral into the sun, and who wants to help? So, yeah. Well, so just to sort of follow on this, we actually talked about this in an earlier episode of Astronomy Cast, talking about this idea of moving the Earth in the far, far future of the solar system, that you could have asteroids make really close flybys to the Earth, and we could slowly raise its orbit, and that's what you're doing. But in this case, the Earth is stealing the orbital momentum from these asteroids, and then it's using that to increase its velocity, and by doing so, it raises its orbit. So I think someone did the math. It was like, I forget, like 10,000 or 100,000 asteroids. You would literally need to have an asteroid make a close flyby of the Earth every 1,000 years until the end of the sun, 5 billion years from now. So more than that, way more than that to kill Jupiter. But I think it's worth it. I really do. Just push Jupiter into the sun and be done with it.
I like Jupiter. I don't want to kill Jupiter. It has a big red spot.
All right. Ooh, okay, so Ilad Avron says, Superman apologists actually have a good argument for it. I'll post it in the event comments. Please do. I think I want to continue this conversation.
I just like the fact that they're Superman apologists. That kind of made my day.
All right, so Ilad, if you've posted that. All right, so... Okay, so here's what he's saying. So Superman apologists say that it's actually not that Superman is stopping and reversing the Earth's rotation, but that he's flying so fast that he started moving backwards in time, and relatively the Earth seemed to have stopped and reversed rotation, but it's just an observational, whereas he himself was the one going back in time. What do you think?
I think that we will all enjoy Superman more if we don't think too hard about it.
Oh, you are no fun. All right. Let's see if I got anything else. Rashan Bakari also asks, does light experience inertia? And if not, why not?
Yeah, it does.
Good one. Okay. But on a photon by photon level, I guess.
Yeah. It's a particle.
And so right, and so
you
how
end up with
much
light
effort
orbiting, you end up with light orbiting black holes.
Which kind of gets to the heart of what inertia is, right? Because light orbiting a black hole, it's following the curvature of space-time as distorted by the black hole.
Yeah. It's all cool.
Yeah.
Over on Twitter, Josh Andrews, whose Twitter handle is JoshURTree, said, I feel the Superman anti-rotation question needs to be sent to XKCD.
Yeah, is it what if on XKCD?
Yeah.
It's the best thing ever.
Yeah.
All right. Well, I think those are all the questions that I can see. If anyone has any more questions, now's your time. But I will, why don't we wrap this up? So is there anything we want to promote?
There is sign-ups for a Cosmo Academy class, I believe, on astronomy and poetry right now that everyone should go sign up for your daily dose of humanities. And I think that's about it right now.
Okay. There is something happening that I don't think I can announce yet, but I will announce it very quickly, and it's going to happen very quickly, and you can find out about it by, I don't know, follow me on Twitter or Google Plus if you haven't already. I will try and get the word out on all the places and Universe Today. So as soon as
big announcements.
I know I'm sorry I can't be more specific, but it's super, super exciting. So, so stay tuned.
As long as you're sorry instead of sorry.
Sorry.
Canadian.
Yeah. All right. Well, let's wrap things up. So, Pamela, once again, thank you so much. I appreciate we didn't have to do math. We got very close. I could feel math was about to get cracked out, so that was good. Thanks to everyone who watched. Another recommendation, go check out the WSH crew for One Community, and as well as the CosmoQuest forums, cosmoquest.org/forums.
And do science on CosmoQuest. It's not just forums. We do science, and it gets published in journals.
Yeah, absolutely.
So go do science, please.
All right.
Actually,
and follow Pamela on Twitter.
I challenge all of you to go out and do 10 images on CosmoQuest, and I will look for a statistical bump. So I expect to see a statistical bump caused by all of you. So go do science.
All right. You could tell. All right. All right. Thanks a lot, Pamela. We'll see you. We'll see you next week.
Okay. Bye-bye. Go by, and I had a friend on the ground that I was talking with back and forth on iMessage, and it was one hell of a day Friday.
I realized I forgot one thing. If you give me 1 second, I'm going to move a phone, or else there might be problems.
Okay. And I get left alone with all of you. What can I do? It's not like I can corrupt you the way I corrupt other people's children. If you're ever given the opportunity to steal someone's children, teach them to walk around going, exterminate, exterminate. Okay, Fraser's back.
All right. Okay, cool. Well, let's get rolling. So if people have no idea what it is that they have stumbled into, we're going to be doing a live episode of our weekly podcast, Astronomy Cast. So we will be covering today's episode 356, is Inertia. So we're going to talk about this, and then we will stick around for about 30 minutes. Well, we'll stick around until the end of the hour and answer your questions about. There.
Are we live?
All right, now it's working. I don't know. Are we? Can you hear me?
I can hear you, and there's no lag. It's so exciting.
I'm seeing a little lag, but not like a horrible amount of lag.
It's not the 2.5 to 3 seconds we had last week.
No, we can actually have a proper conversation with each other. So I think this is still a vast improvement. But clearly there's still gremlins somewhere in the internets. So how are you doing, Pamela? What a tough week in space.
It really was. Last week was pretty horrible between the Antares incident on Tuesday and then Spaceship Two on Friday, and our hearts go out to everyone involved with both of those missions and out at orbital systems or
about space astronomy. So you can use the Q&A app, and it appears to be working this week. So my additional checks and procedures are working. So you should see, if you're wherever you're watching this video, it's say like Fraser Cain is interacting with the audience, and you can click there, and then you can post a question in there, and if I see them during the show, I'll incorporate them into the show. But otherwise, we'll answer some of your questions afterwards. And you don't just have to ask questions about the topic that we're doing. You can talk about whatever you want. So, okay, great. Are you ready to go?
I think so. I never know what you're going to ask, so that's a very hard question to answer.
Do you understand inertia?
I believe so.
Well, then we'll be fine.
Okay.
Don't worry about it. I'll throw you a bunch of softballs. No problem.
Okay.
All right, here we go.
I am pressing record. I have pressed record. It is recording in stereo. Damn it.
It's a pilot error, whether it was done as whether it was done automatically. They're still trying to get to the bottom of this. So, it was weird on Friday. We were doing the weekly space hangout, and about an hour before we started the show was when this accident happened. And so we were. It was my first time covering something live, and it was quite an experience. And then we were really fortunate to have Ken Creamer, who was reporting, who was actually at the Antares explosion, and he was there, and he gave his first-person account, and it's really riveting. So if you haven't already watched Friday's episode of the Weekly Space Hangout, I highly recommend it. I like to think it was a pretty good episode, and you really get a great description from Ken about what it must have been like to be right there then.
Yeah, so. I have to admit, I was going back and forth between watching you guys and watching CNN and watching the tweets go Orbital Sciences rather and Virgin Galactic and Scaled Composites. It was tough, and we I'd like to point out that there's actually a fundraiser going on to raise funding for the family of the pilot who was lost on Spaceship Two.
Yeah. Are there any details on that? Google it, I guess. I'm sure you can find out.
Yeah, there and in terms of details on what happened, they've identified that for whatever reason, the feathering device that turns it from a space plane into a badminton birdie decided to deploy early, and that sudden attempt at deceleration just tore it all apart.
Right. Well, I mean, it's still early stages, and so I think, the question, the controversy still right now is whether it was